Hello and welcome to this edition of Tech Talk. This is where we bring technical experts from Cisco to share their insights on specific topics selectively chosen based on most common conversation themes on our technology area. It's an effort to share valuable insights from Cisco experts on those popular topics. We hope you like it. My name is Satish Chandran and I'm the community manager at Cisco, and today our topic for discussion will be ASR9k, life of a packet and troubleshooting packet loss. Our experts joining me today are from Cisco High-Touch Technical Support HTTS team. They have been supporting major service providers and large enterprise customers for routing, MPLS, Multicast, and Layer 2 VPN issues on all routing platforms. To my left, Hitesh Kumar, a customer support engineer with CCIE in service provider, and he's an iOS XR specialist. Welcome, Hitesh.
Hello, Satish. Hello, everyone.
Thank you. And towards his left is Rahul Rammanohar. He's an escalation engineer, and he's a double CCIE in routing and switching and service provider. Welcome, Rahul.
Hi, Satish, and great to be here.
Great. And we have Vinay Kumar, a customer support engineer with CCIE routing and switching certification, and he's also an iOS XR specialist. Welcome, Vinay.
Thanks, Satish. Pleasure to be here.
Great. So ASR9k is a next generation service provider router, and market seems to be very excited about it, isn't it?
Yes, definitely. I agree with you, Satish. We have been providing support to world's leading service providers and large enterprise customers for many years now. As majority of these customers are transitioning to XR platforms in the network, we wanted to discuss about packet flow and troubleshooting packet loss on the ASR9000 series routers. Cisco ASR9000 series routers were introduced in two form factors, the ASR9010 and the ASR9006. The ASR9006 is a 6-slot chassis which can provide throughput up to 1.7 terabits per second, and the ASR9010 is a 10-slot chassis which provides throughput up to 3.5 terabits per second. Cisco later introduced the ASR9001 and 9922. ASR9001 chassis provides throughput up to 120 gigabits per second, and the ASR9922 can provide throughput up to 15 terabits per second. With the introduction of network virtualization on the ASR9000, Cisco introduced the ASR9000V, which is a 44-port, 10,100,000 port satellite device and operates as an extension shell to the ASR9000. Now let's go talk about the very big one, that is ASR9922. ASR9922 has dedicated switch fabric cards and separated route processor, very much like CRS and GSRs. It allows you to build a scalable system as it increases capacity per slot. ASR9922 has been designed to support up to 7 fabric cards in 6+1 mode. So even if one fails, 6 can function without any service disruption. ASR9000 runs next generation iOS XR software, which is highly secured, scalable, and modular network operating system, which allows uninterrupted operation. Let's start with building blocks of ASR9006 and 9010 chassis. On ASR9k, we have the route switch processor, which has both switch fabric and the route processor, and they are logically separated. Cisco recommendation is to have 2 RSPs in a single chassis, with one being active and the other being standby. For ASR9006 and 9010, RSP comes in 2 flavors, that is RSP2 and RSP440. RSP2 has a dual-core PPC processor, each core running at 1.5 GHz, and RSP440 has a quad-core Intel processor, with each core running at 2.27 GHz. For ASR9922, the CPU same as the RSP440. RSP is mainly responsible for management and control plane functions. Each RSP has a switch fabric, which provides non-blocking data connection among line cards and a connection between the line cards to the RSP for control packets. Here we have 2 RSPs, RSP0 and RSP1, both being RSP440, showing the integrated switch fabric. One RSP remains active and the other being standby.
So let's take a look at the line cards now. So the ASR9000 is a fully distributed architecture where all forwarding decisions are taken by the line card, and the RSP does not have any forwarding engine. On the line card, data forwarding is handled by multiple network processors, or NPs. Each NP caters to a set of ports or a single port based on the type of line card. There are two generations of line cards. The first generation uses the Trident network processor, and the second generation uses the faster and more scalable Typhoon network processor. The first generation line cards support either 40 gig or 80 gig of I/O. The 40 gig cards have 4 network processors, and the 80 gig cards have 8 network processors. The cards that have 4 network processors are the A9K 40GE, the A9K 4T, the A9K 2T20GE, and finally the A9K 8T/4, which is an 8-port 10 gig oversubscribed card. The cards that use 8 Tridents are the A9K 8T and the A9K 16T/8, which is a 16-port 10 gig oversubscribed card. All the Generation 1 cards also come in 3 scale types: a low Q, a medium Q, and a high Q type, which have been created for various markets. The main difference between the 3 types of cards is the amount of TCAM memory available for the Trident processor. The second generation line cards support a lot more I/O bandwidth than the first generation. We have the A9K 2X100GE, the A9K 1X100GE, the A9K 24X10GE, and the A9K 36X10GE, which is a 36-port 10 gig card. There are also 2 carrier cards based on the Typhoon network processor: the A9K Mod 80 with a bandwidth of 80 gig, and the A9K Mod 160 with a bandwidth of 160 gig. From a scale point of view, all the second generation cards come in 2 flavors: the TR and the SE, created for different markets. Again, the main difference between the two is the amount of TCAM memory available for the Typhoon network processor. Cisco recommends buying the second generation line cards. Please take a look at our blog and the ASR9k datasheets on CCO for more details on all these cards. Each line card has its own CPU, which handles some of the control plane functions of the router. The CPU on the Generation 1 line card is as powerful as the RSP2, and the CPU of the Generation 2 line cards is as powerful as the RSP440. We have 2 cards showing up on this slide. The top line card is the A9K 4T. It's a 4-port 10 gig, which is an example of a Generation 1 line card, and the bottom line card is the A9K 24X10G, a 24-port 10 gig card, which is a Generation 2 line card.
So is there any other difference between the Generation 1 and Generation 2 line card?
So let me take this question, Satish. So apart from having a more powerful network processor, the Generation 2 line card provides more bandwidth on the backplane. Generation 1 line card connects to the RSP switch fabric via a fabric interface ASIC or FIA. These line cards comes either with 1 or 2 FIAs. FIA connects to the switch fabric with 4 fabric links, each of which is of 23 gig. So the card with 1 FIA provide a bandwidth of 92 gigabit per second in each direction, and the card with 2 FIA provide double the bandwidth, which is 184 gigabit per second in each direction. On the other hand, the Generation 2 line cards have 8 fabric links to the RSP switch fabric, and each of this is of 55 gig. So providing a total bandwidth of 440 gigabit per second in each direction. So clearly we see more bandwidth with Generation 2 line card. Hope that answers.
Sure.
Okay. So we have another member in the ASR9000 family, which is ASR9001, and here is the block diagram. It is a compact 2-rack unit router with an integrated RP, switch fabric, and line card that provides a throughput of 120 gigabit per second. ASR9001 is a combination of RSP440 and Mod 80 line card. That's why you would see 2 CPUs here, one LC CPU and the other RP CPU. This router also has 4 inbuilt 10 gig SFP plus ports, which you can see on the left side, and also 2 slots for MPAs, or we call it modular port adapters.
So is the MPA similar to SPA?
So the SPA or the SPA is a shared port adapter which has been designed to support a maximum bandwidth of 10 gigabit per second. Most of the non-Ethernet based SPAs are supported on the 9006 and 9010 chassis, only when using the SIP700 carrier card. The SIP700 supports either 4 half-height SPAs or 2 full-height SPAs. Keeping the growing need for bandwidth, the MPA has been designed to support a maximum bandwidth of 40 gigabit per second. we currently have MPAs in different flavors like the 2 and 4 port 10 gig, the 20 port 1 gig, and a 1 port 40 gig, with more being released. The MPAs are also supported in the second generation carrier cards, the A9k Mod 80 and the A9k Mod 160. Hope that answers your question.
It does, thank you.
So now let's look at the Unicast packet flow. The ASR9000 uses a two-stage, fully distributed forwarding architecture. The ingress NP performs the first stage and the egress NP performs the second. The active RSP maintains the routing information base or RIB and the label switch database or LSD, which it creates from information it receives from LDP, RSVP-TE, BGP, and other routing protocols configured on the router. These databases are then passed on to the line card CPU for creation of the forwarding information base or FIB. The ARP process runs on the line card CPU, from which the adjacency information base or AIB is created, which includes local adjacency information only. The line card CPU programs the network processors with the FIB and adjacency information, which the network processors utilize for packet forwarding.
Let me show you the Unicast packet flow. On the ingress line card, NP receives the frame from the physical media. It performs the first stage packet lookup and is responsible for all layer 2, layer 3 forwarding decisions and feature processing like ACL and QoS. From the ingress lookup, we get the information about the egress NP. The frame is then forwarded to the bridge ASIC. Bridge ASIC translates the header to a format that the fabric interface ASIC or FIA can understand and forwards the frame to the FIA. FIA connects to the fabric and the frame is sent to the egress line card via the fabric. The egress NP performs a layer 2 rewrite and applies all the egress features like ACL and QoS on the frame and sends it on the wire via the physical media.
So I have a question here. Why there is no bridge ASIC on generation 2 line card?
So the network processor on the generation 2 line card can directly speak to the FIA, which is fabric interface ASIC. So we don't need any bridge ASIC for any kind of translations. Hope that clears.
It does.
Okay.
Thank you.
So let's take another example of Unicast packet flow, which is local switching. So with local switching, we mean we have source and destination port that are on the same card, but the packet still travels to the switch fabric on the RSP. In this example, we have a source port which is connecting to the NP0 of the generation 1 card and the destination port NP2 on the same card, but the still packet goes to the switch fabric on the RSP before it is being sent out of the destination port. Same is true for the generation 2 line card as well, where we have its internal switch fabric. We have a source port connecting to the NP1 and the destination port is on NP3, which on the same card, but still the packet goes through the RSP switch fabric and then it goes out of the destination port.
Okay, so you guys talked about the transit traffic. What happens to the packet that is destined to the box itself?
Okay, I was expecting this question, Satish. So for the packet which is destined for the router, we have a process called LPTS or Local Packet Transport Services, which is an integral component of iOS XR system. It enables the router to act as a distributed system, which means we can run various protocol processes across the RP and the LCs. So what happens is ingress NP receives the packet which is destined to the router. It performs a FIB lookup and forwards the packet to the LPTS. LPTS uses its pre-FIB table to determine whether the control packet needs to go to the LC CPU or it is meant for the RSP CPU. So LPTS handles traffic like ICMP packets, management plane traffics like Telnet, SSH, XML, and the control plane traffic such as OSPF, ISIS, BGP, LDP. Important thing to remember here is that not all the packets destined to the router will go to the LPTS. And the example packets are LACP, ARP, BFD, and NetFlow sample packets which are sent directly to the LC CPU.
One of the biggest strengths with LPTS is the dynamic ACL creation, which is configuration driven and with no user intervention. Let us take BGP as an example. When you have no configuration, we would have a fixed polisher handling traffic for TCP port 179 with any destination and any source address which is heavily policed. As you configure and start to bring up a BGP session, an entry is dynamically created with the source address, which is a local address, and port 179 that is moderately policed. Once the session is established, another new entry is created for the L3 and L4 data that is lightly policed. Multiple such bindings would be present on the network processor till the session dies out. LPTS also polices the incoming packets destined to the router. This policing mechanism is similar to COP or control plane policing found on other platforms that is needed to protect critical applications. These policer rates are predefined for different flow types and are applied to the control and management plane traffic destined to the router. LPTS can be configured on a per line card basis, and this will affect all the network processors on that line card.
I'll explain LPTS with few examples. Say ingress NP receives a BGP packet. It performs the fib lookup and sends the packet to LPTS. LPTS performs the lookup and forwards the packet to the RSP CPU. Now the ingress NP receives another packet that is destined to the local CPU. After a fib lookup, the packet is sent to LPTS, and the packet is forwarded to the local CPU. LPTS also handles control plane policing. So if the ingress NP receives a packet that exceeds the policer rate, it would get dropped by the LPTS.
So you also spoke about Unicast packet flow, but how about multicast traffic? Is it handled the same way?
Okay, let's discuss the multicast packet flow. Multicast related processes such as PIM, IGMP, and the MRIB or the multicast routing information based process are running on the RSP CPU. Hence, the multicast PIM and IGMP control packets need to be forwarded by the line cards to the RSP CPU. The MRIB process is responsible to build the multicast RIB table based on the information from PIM and IGMP. The MRIB table will be downloaded to the MFIB process, the multicast forwarding information based process on the line card CPU. This MFIB process will program the hardware tables on the network processors, bridge ASICs, and FIAs. These hardware tables, which include the MFIB table, the multicast group ID table or MGID table, and the fabric group ID or FGID table, are used by the various ASICs for multicast replication and forwarding. Also, software switch packets are sent to the local line card CPU if the host is present on the same line card, else the packet has to be forwarded to the RSP.
Excellent.
Okay, let's take an example of multicast flow now. So we have a one source S1 connecting to the NP0 of our generation 1 line card, and we have 5 receivers. One of them is on the same line card and 4 are on the generation 2 line card. The packet is received by the Trident, which performs the RPF check, determines the FGID, which is fabric group ID, and MGID, which is the multicast group ID, performs the feature processings like ACL and QoS, and then forwards the valid packets to the switch fabric on RSP. In ASR9k, there are 4 planes where the replications takes place, and the first being the switch fabric, which is shown as S1 here. It replicates the packet to the appropriate line card using the fabric group ID or FGID. The line card receives the packet on the fabric, which performs the second stage of replication and sends the packet to the FIAs. FIAs performs the third stage of replication, and it replicates the packet to the corresponding MPs based on the MGID or multicast ID. Network processor receives the packet, performs the feature processing like ACL, QoS, and replicates the packet to the corresponding interfaces. This is the final stage of replication. Same process applies to both L2 and L3 multicast. And the best part about the ASR9k is that it performs intelligent replication on all the stages.
So what do you mean by intelligent replication?
The box is an intelligent one. Let me explain you the meaning of intelligent replication. On ASR9k, replication is only performed on the egress line card, and that too at places where it is required, that is where subscribers are present. In the same example, at step S3, the FIA0 replicates the packet to both NP0 and NP1, as there are subscribers connected to both NP0 and NP1. FIA1 only replicates the packet to NP3 and not to NP2, as there are subscribers present on NP3 and not on NP2. Now let's talk about the fabric path. The switch fabric are present on the RSPs and always remain in active-active mode, though the RSPs work in active standby mode. This means the fabric on both RSPs is available for data forwarding, hence Cisco recommends using dual RSPs. With the Generation 2 line cards, Cisco introduced a 3-stage fabric, which provides better scalability, and hence the Generation 2 card has its own fabric. However, packet flow remains the same as the Generation 1 line card. In our example, we are using 2 RSPs, that too RSP 440. Hence, a Generation 2 line card will have a bandwidth of 55 gigs for each of the channels. In case we were to use a Gen 2 line card with RSP2, the bandwidth will drop to 23 gig for each of the channels.
Another intelligent feature is that the line card's access to the RSP switch fabric is controlled. Each RSP has an arbiter ASIC acting as a supercop. The arbiter on the active RSP is active, and the other arbiter silently listens. Before the FIA sends a packet to the switch fabric, it will send a fabric request to the arbiter. The arbiter will check if there is available bandwidth on the egress line card. If yes, it will grant access to the ingress FIA. Arbitration makes sure that there is bandwidth fairness among the line cards. Now, let's look at how Unicast packets are load balanced across the fabric. Unicast traffic is sent across the first available fabric link to the destination, which maximizes efficiency. Hence, load balancing of Unicast packets is per packet. Each frame contains sequencing information added by the ingress FIA, and all the egress FIAs have resequencing logic to avoid out-of-sequence flows.
And what about the multicast load balancing?
Okay, so as compared to the unicast traffic, multicast packets are load balanced per flow, which means for a particular S, G entry, a packet will always take the same link. However, for other, it will take different link. So now let's take a look at the troubleshooting section. So one common problem that we see in all networks is the packet loss. In order to troubleshoot packet loss issues on ASR9k, it is very important to isolate where exactly the packets are getting lost in the system. To troubleshoot, we should look at the following places. The first one would be PLIM, which is physical layer interface module. The second one would be network processor or NP, bridge ASIC for generation 1 line card, FIA, which is fabric interface ASIC, and finally the switch fabric. Once the problem location is identified, we can take the corrective action. So let's take a look at the slides now. We'll look at the PLIM and check the commands like show interface, and we should see like input errors, input drops, output drops, and CRC errors. Then check the controller stats and look for kind of drops like input drops overruns, input drops aborts, and the same thing is true for the output as well. Next we go to the network processor and check the first command, and that will allow you to understand where exactly the interface connecting to the NP. And then you can use the remaining commands to check their counters to understand if there are any kind of errors or drops happening. Next we go to the bridge ASIC. Bridge ASIC is used only in the generation 1 line card, and you can use the fabric FIA bridge stats to understand if there is any problem with the bridge ASIC. Then we come to the FIA, which is fabric interface ASIC, and your fabric FIA stat location command help you to understand what kind of drops and errors are coming. In case you only want to see the drops or errors, you can use the individual commands, which are the command 2 and command 3, and you can use it for both the ingress and egress location to understand are there any drops or errors happening. You can also see any kind of congestion happening via the last command, which is fabric FIA queue depth location, and see if there are packets getting stuck into the queue. And last but not the least, we come to the RSP switch fabric. And these crossbar statistics instance command help you to understand if there is something wrong with the RSPs. More information about these commands and the outputs can be seen with our blog.
Okay, great. So that concludes our today's presentation. And thank you, Hitesh, Rahul, Vinay.
Thank you.
It was a great presentation with a lot of animations. I hope users will really understand, with all those animations. So, hope this tech talk on ASR9k life of a packet and troubleshooting packet loss was useful to you, and we look forward to your feedback. You can send in your feedback using the comment section. You may also ask questions and collaborate via various social media channels like Facebook and Twitter. You can also catch us on YouTube, Google+, and LinkedIn. Goodbye, and thank you for watching.